Okay, Omstar, you'll be here soon and we won't need to do this every single class, so hope you're well. Does anyone know when Om is coming? Tomorrow, is she? Not sure. Anyway, let's quickly revise. Let's revise chapter 3. Where do we start? Let's quickly, so really we just need to go through those tests in our mind, don't we? First test. Yeah, well I reckon one way is we can, we looked at forming a sum. So yeah, well I suppose we could look at, okay, yeah. Let's look at the divergence test. Susan, can you remember what the divergent test is? You know, yeah, it's a limit as k approaches to infinity of uk. If that doesn't equal to 0, then that series will diverge, yeah? That was the first one. Then the second one we talked about was a comparison test, wasn't it? So, comparison test. What are the two main comparisons that we often use? We compare to a p-test. Yeah? So what I'm saying is here we'll compare with a p-test. Or, what's the other one that might strike you? If it's not a p-test, sometimes it's a geometric. Yeah. Sometimes it's a geometric with a common ratio less than 1. Yeah, that will converge or diverge. Yeah. So they're the two main things we use the comparison test for. If we can't directly use a comparison test, if we can't create that inequality, then we need to use the limit comparison test. So it's very close. It's just in those times when you know it's going to be a comparison test just won't work, but you still know it's going to converge or diverge, then we use a limit comparison test. Limit comparison test. Great. Let's just write down what that is. That's the limit as k approaches infinity of ak on bk, and if we take that limit, and that limit is, what are we saying? It's greater than 0. Yeah? If one series converges, then that will converge. If that diverges, that will diverge. Yeah? So we use that. Okay, after the limit comparison test, what was next? The integral test. Yeah? The integral test. What is the integral test? If we form a function from a sequence, in other words, if we do this, if we have a sequence, and that sequence is, how can I say this? If this sequence might be a function in k, yeah, that's what I'll do. If that sequence is a function in k from, say, a up to infinity, yeah, what we can do is we can check out that, yeah, by writing the integral from a to infinity, the improper integral, as a function of that in x dx. If this integral converges, then that will converge. If this integral diverges, then that will diverge. So it's that straightforward. Yeah? If the integral converges to a real limit, then so will the sum. So don't forget though to write that in terms of x or some other variable that's different from that k. So that's the integral test. Next, after the integral test, what do we do? Yeah, we did an alternating series test. Very good. Hope this is not wasting your time. What's the alternating series test? Two conditions. Just quickly, just in your mind, two conditions are that it must be decreasing. In other words, UK plus 1 must be less than UK. What's the other way to test decreasing? Yeah, to check that F dash K might be less than 0. Yep, so we could find the derivative of that sum, or that, you know, that sequence expression, and show that that's always less than 0. So it's always decreasing and positive. And what's the second test? Is just to find out, to say, does the limit as k approaches infinity of UK equal to 0? So they're the two conditions for the alternating series test. Then we talked about conditional and absolute convergence. What is conditional convergence? Where the alternating series is convergent, but the absolute is not. So this is conditional is, if you like, the alternating is convergent. Yeah, but the absolute is not. Can you think of one? What's the most obvious one that's conditionally convergent? Yeah, that's right. This one here is conditionally convergent, isn't it? That one there. What's absolute convergence is where if it's absolutely convergent, it's convergent. So absolute convergence is just a straightforward, if it's absolute, it's convergent. So basically, if absolute, yeah, then it's convergent. So if it's absolute convergent, then it's just convergent. Next. Not terribly important. Does anyone remember why conditionally convergent was important? Do you remember talking about that? Why was that important? If you rearrange the terms, you can create a contradiction, can't you? Do you remember that, when I rearrange the terms? So conditionally convergent is interesting because if you do rearrange, you can create a mathematical contradiction. Last thing, what did we do then? We did the ratio test. Yep, what's the ratio test? Well, we've just done that, so that's the limit as k approaches to infinity of UK plus 1 on UK, and we've got some conditions for that, haven't we? If it's less than 1, if it's greater than 1, or if it's equal to 1. So we're just exploring what happens at infinity, aren't we? If at infinity the common ratio is less than 1, then those terms at infinity are going to converge. And before infinity, well, that's a real number. If we add up real numbers before infinity, we get a real. So if we add those two together, we get convergence. So that's the ratio test. When do we apply the ratio test? How would you know how to apply the ratio tests? If you get, say, k factorial, if you've got factorials, or you've got a to the power of k, yeah, or k to the power of a, that sort of thing should ring sort of bells, and you should say, yeah, did I press record? Yeah, you should, that should ring bells and say, yeah, I need to use the ratio test. We need to use the ratio test when we find when we investigate the radius of convergence or the interval of convergence. Yeah. So the last thing we looked at was radius of convergence. Radius of convergence, and the other one was the interval of convergence. Yeah. Three conditions, three things can happen with the radius of convergence, isn't there? One is, we'll just quickly write these, the radius of convergence can equal to 0. If it does, what does that mean? The series will converge for just one value of x, won't it? So the series will converge just for one value of x if the radius of convergence is equal to 0. If the radius of convergence is equal to infinity, yeah, then what does it mean? It will converge for all values of x. X is an element of any real numbers. And what was the last condition? Of course, the last condition was it only happens for an interval. And what do we need to do with that interval? We need to check the endpoints of the interval. In other words, we might have a number line here. We've got b here and we've got a here. So there's a and b. We just need to check that interval to find out whether this is we include a or we don't include a, or we include b or don't include b. Yeah? Generally this side here will be what? Alternating? Yeah. Generally this will be an alternating test. Well, it's hard to say. It depends on what the series is, okay? And that's chapter 3. Now, it's probably not a bad idea if you want to take a photo of that or record that somewhere. I've got a great mind map of all of this here. Yeah, I've got a great mind map. The thing will be hard for me to do this in my head in a couple of weeks because I won't necessarily be able to do it as clear because I've just, having taught it in the last week or so, it's nice and clear in my head, so I can just rip that out. But in a couple of weeks' time, it may be a little bit more lucid, unclear. Okay. Move on. Are you okay, Diana? Good. I'll just see if I can get a better black texter to move on with. Oh yeah. Oh yeah. Right. I'm going to rub that out. Good, let's do this. There's that chapter, gone. And this must feel good for us to write up chapter 4, which is looking at Maclaurin series, Maclaurin and Taylor series, really. So let's look at the next chapter, which is the Maclaurin and the Taylor. Can't spell Taylor. Oh, yes, I can. Taylor series. Maclaurin and Taylor series. Do you remember yesterday we talked about a particular example? If I had, well, let's just say the one they give in the textbook is this. I think they have f of x is equal to 1 minus 3x to the power of minus 1. Yeah, I did this one yesterday. Oh, it's plus. It's plus. So the idea here is, if I have a function, can I write a function as a series? Here I have a function, f of x equals to that. Can I write that as a series? And we sort of did this yesterday, didn't we? Do you remember doing that? Because what I can do is I can say, oh, this here equals to 1 divided by 1 minus negative 3x, like so, all to the 1 then. Agree? So I can write that function like this. If I write that function like this, you'll probably recognise a couple of things. This looks very, very similar to the sum of a geometric series. In other words, this is a sum to infinity. where this term is a equals 1. Yeah, and my common ratio down here, ladies and gentlemen, my common ratio is equal to minus 3x. Yeah? So what would my series be for this? So my series for that, so f of x can now be written as a series which is, let's do this, 1 minus 3x plus 9x squared minus 27 x cubed plus 81 x to the power of 4 minus dot 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 dot. So we can now write a function as a series. Does anyone know for what values of x this function here, yeah, what values of x that will converge? What values of x will that converge to? Well, we could do that, couldn't we? I mean, we did this last year. This is kind of a common ratio question, isn't it? What's the common ratio? Minus 3x. So we've got the absolute value of minus 3. Absolute value of minus 3x is less than 1. Which means minus 1 is less than x, which is less than 1. Minus 3x. Divide by negative 3. So we'll end up with 1 is going to be greater, 1 on 3 will be greater than x, which will be greater than minus 1 on the third. So I don't like writing it like that, so I'm going to write it like this. So for what values of x will that converge? It will converge between values of x between minus a third and a third. Agreed? So that series, this series here will equal to that function when the values of x are trapped between. What's the radius of convergence? What's the radius of convergence? A third. Very, very good. Well done, everyone. What's the interval of convergence? Can I include this and that? No, I can't. So the interval of convergence is just that, really. There's my interval of convergence there. But there's a radius of convergence there. Well done, everyone. Could I write this in some notation? Equals to the sum of what? What are we going to start k as? Start k as 0? Yeah? So we'll go from 0 to infinity. And what do I have to put here? I'd have to put a k in there, wouldn't I? Minus 3 to the power of, minus 3x to the power of k, isn't it? Is it? Yeah. So it'll be minus 3x, minus 3, x to the power of k. So now you can see what we've done here in this case, and believe it or not, sometimes this is a very legitimate way the IB likes to, because the Maclaurin and the Taylor series, as we're going to show you in a sec, Xavier, I'm going to show you in a moment, using the Maclaurin and the Taylor series, we can take any function we want and turn it into a series. Now sometimes you don't need to do that, because sometimes the functions you've got can be written as a geometric series, so be very, very careful. Sometimes this is a much quicker way than doing all what I'm about to show you. So there's not a lot of practice of that, but maybe in the old syllabus, which I used to teach in that old syllabus 10 years ago, that was a very common thing, and they wouldn't tell you that, hey, you don't need to, as we'll find it in a moment, we can make a series, but this technique, the Maclaurin and the Taylor technique, can be very complicated because you've got to find what's called multiple derivatives. Now, if you don't need to use that method, and you can simply equate it to a infinite geometric series, it's much quicker. So sometimes that could happen in an exam. Yeah, and you'll see 1 or 2 examples of that going over the past papers. This is a very quick way, as you can see, very quick way to write a series. There's a very long way, and I'll show you that now in a moment. However, generally speaking, they don't do this, but sometimes I've seen that they do. Does that make sense? You know, probably doesn't make sense because you haven't seen that. But my point is, I've got a function, and I can write a series to that function, right? But, of course, this is the only situation that I can do that if I can recognise it as geometric. I want to be able to do it for any single function at all. So what I'm going to do first of all is I'm going to create that, and you'll notice, okay, so I'm going to create a function based around the point x equals to 0. And this is how I'm going to do it. Are you ready? So I'm going to say f of x is some sort of series. And this series goes like this. It's a0 plus a1 times x plus a2 times x squared plus a3 times x cubed. I'm going to write a function as a series. And there's my series there. If you like, it's a polynomial-based series, isn't it? Is it possible to write a function as an addition of polynomials? And the higher degree the polynomial I get, the more accurate this series approaches that function. So what I'm going to do though, is I'm going to, this function that I'm trying to write a series for is going to be based around a point. It's going to hinge around a point. And that point is called x equals to 0. So in this case, I'm going to find a function. I'm going to find a series from a function, and this series is going to be equivalent to that function and accurate to that function around the point x equals to 0. So I'm going to investigate. I'm going to investigate a series that is equivalent to the function at x equals to 0. Sometimes we can say the series is equal to the function, but we can only do that under certain conditions. So let's start off. Okay, the first thing I'm going to do is I'm going to say this. What is f of 0 equal to, everyone? What's f of 0? So here's, what's f of 0? F of 0 is going to be, in fact, let's add on another one here. What's f of 0, ladies and gentlemen? F of 0 is equal to a0. Fantastic. Great. What's f dash x equal to? If I was to find the derivative of that, what would I end up with? a1. Yeah? Plus 2 times a2 x plus 3 times a3 x squared plus 4 times a4 x cubed. Cool? Good. What's f dash 0 equal to? A1? Very good. So, very importantly, I found, hey, A0 equals to f of 0. A1 is equal to f dash 0. Good. How about if I was to find f triple dash x? What's that equal to? Sorry, f double dash x. F double dash x, let's differentiate this again, and I get 2a2 plus, now notice here, 2 times 3, so I write this as 3 times 2 a3x plus 4 times 3 a4x squared. Cool? What's f double dash 0 equal to? 2a2. This implies, maybe I'll do that on the same underneath so it makes sense. So what's a2 equal to? F double dash 0 divided by 2 equals to a2. I think in the next one you'll see the pattern, ladies and gentlemen. Let's do f triple dash x. So f triple dash x equals to 3 times 2 times 1, a3, plus 4 times 3 times 2 a4 x to the power 1 plus dot 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 dot. What's f triple dash 0 equal to? Yeah, 3 times 2 times 1. What's another way to write that? 3 factorial times a3. Now, I'll just write this here because I'm just running out of space. I'll write a3 is equal to f triple dash 0 divided by 3 factorial. Can anyone see what a4 is going to equal to? Are you with me? What's a4 going to equal to? So this is what a3 equals to. What's a4? Can you see the pattern? I think some of you probably can. If I differentiate this one more time, I get 4 times 3 times 2 times 1 times a4 is equal to f fourth derivative of x, isn't it? So if I was to differentiate this one more time, I get f fourth derivative of x is equal to 4 factorial a4. With a 0 in there, sorry. Yeah? So, a4, the coefficient a4 is f for x divided by 4 factorial. And I'm just swapped in a Roman numeral there. Generally that's the case. We don't put 4 little dashes there. We use Roman numerals when we do higher order derivatives like so. Yeah? So f5 is fv. Yeah, x, okay? So you can write a 5 there if you want, or a 6 or a 7, but generally speaking, we use Roman numerals there. I don't know why. Not sure a Roman made this up. Maclaurin, sounds English to me. So, I can now write this function, can't I, as a series. And I might do it over here. Will I? Yes, I will. Here we go. So f of x is equal to, what's a0? a0 is f of 0. Good. What's a1? a1 is f dash 0. What's a2? a2 is f double dash 0 on 2 factorial. X squared. What's a3? F triple dash 0 x cubed on 3 factorial. What's the next one? F 4 0 x to the power of 4 on 4 factorial plus dot 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 dot. And there we have what is known as our Maclaurin series. Yeah. Could I write that in series form? Could I write that as a series, do you think? What would we say? That's going to equal to the sum from 0 to infinity. Yeah. It will be f to the power of k. The 0 derivative means we don't find the derivative of it at all. F to the power k 0 times x to the power of k divided by k factorial, and there's my series definition of a Maclaurin series. Thank you, Diana, that was lovely. Got that spot on. And there we have our Maclaurin series.
That one should be f triple dash 0, not x.
Thank you. Well spotted. Of course, that derivation is not important, Xavier. Yeah? What's important is how you use it. Do you understand what we're doing? What we're doing is we're trying to write any function any function at all, we can now write as a series. However, this series is only accurate about which point? It's only accurate about the point x equals to 0. And as we'll see that in a moment, I'll give you a very good example on the graphics calculator why that's the case. But just before I do, let's use this and show you how it works, yeah? Yeah. If you want time to write that down, go for it, yeah? Do you want to write that down or no? Just take it. I'll give you a good 5 minutes, yeah? I'm happy to do that. The most exciting 5 minutes on YouTube ever. A class copying down. That's from the board. This will bring in heaps of money for me. While we're doing that, I'm going to set up this over here, because what we'll do is we'll get this going in a sec. How'd you go?
Okay.
Good. Well done.
在哪儿了？
Righto. 2 minutes left, everyone.
我靠！谢谢。
Have you done this before, Yilin? No. Do you like this? No.
哎呀，这是啥？第3章讲完了。第3章讲啥？
第三章昨天讲完了。
昨天讲完了。
昨天讲完就讲完。
我靠，这还有一章吗？壁纸就没有了。没有了。
就是它。没有，我刚升上这个壁纸就是这个壁纸，就是它呀。
不一样的呀，它2个虽然都是在揉点，但是揉的不一样。我给你看，我从来之后老开始跟上。你看，这个是这样的，一样的。
Right. Sorry, Mr. Fee. I'll rub off which part. The 2 boxes. Okay, I'll wait. It's fine.
只讲了这些。
You don't mind if we just go that little bit more today? I'm sorry I was sort of 5 minutes late or something. Something like that, 5 10 minutes late. But we might just go a little bit more than an hour today, if that's okay. I just want to do 2 examples, but then I want us to do a more trickier example. Yeah. Some of the things I'm about to do, in fact, the next two examples I'm about to do are in your data booklet. Some of these typical functions are in your data booklet for the Maclaurin series. So I'll show you which ones are. I'll do e to the x, and I'll start it over here, just while Fee's writing it down, because you're almost done, aren't you? Yeah. Let's quickly write, how do we write a Maclaurin series for e to the x about the point x equals to 0? So I want to write a function, e to the x, as a series about the point x equals to 0. So it's going to be accurate, as we'll find out, near x equals 0. The further you are away from x equals 0, the less accurate it gets. Okay, so let's just do this, and I'll show you a picture. Well, actually, maybe I'll show you the picture of the sine graph rather than e to the x. But let's just do this. So we've got f of x equals to e to the x, and I want to write a Maclaurin series. Now, if it says write a Maclaurin series, it means about the point x equals to 0. Yeah? So that's what that means. So what's the formula for the Maclaurin series? F of x equals to that, which is f of 0. I'm just writing it down just so you can see. F dash 0x plus f double dash 0x squared on 2 factorial plus dot 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 dot. So I think I want the first 4 terms of this Maclaurin series. That approximates e to the x. If I use 5 terms, I get a better approximation. If I use 6 terms, I even get a better one than that. So let's just run through the first step. What's the steps I need to do? Well, I need to find what f of 0 is. What's f of 0? F of 0 is e to the 0, which is 1. Great. What's f dash x equal to? E to the x, isn't it? Yeah? Which is also, luckily, what's f double dash x equal to? E to the x. What's f triple dash x? So on. I think you can see every single derivative is going to be e to the x. Therefore, every single derivative, yeah? In other words, what I'm trying to say is, what's f dash 0 equal to? F dash 0 is 1. Good. What's f double dash 0 equal to? 1. Good. What's f triple dash 0 equal to? 1. So on. So all of these here, that's 1, that's 1, that's 1, and so on. So very, very quickly, I think you can see we can write a Maclaurin series for e to the x. What is the Maclaurin series for e to the x? E to the x is equal to 1, yeah, plus 1 times x, plus 1 times x squared on 2 factorial, plus x cubed on 3 factorial, plus x to the power of 4 on 4 factorial, plus dot 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 dot. Cool, isn't it? So, what is the number e? Well, there are many ways to get it. This is one way to get e, isn't it? I've just got to keep on adding to them. For instance, if I wanted to find out what e to the power of 1 is, what do I need to substitute x for here? 1. So let's get an approximation using this Maclaurin series up to x to the power of 4 term for e to the power of 1, shall we? E to the power of 1, well, let's use this Maclaurin series and then we'll compare it to the actual answer. Is 1 plus 1 plus 1 on 2 factorial plus 1 on 3 factorial plus 1 on 4 factorial. So I'm going to get a decimal approximation for what e to the power of 1 is using all those terms. So I'll just leave that graph there and I'll just jump onto my calculator here. I'm not sure if Om can see this, so I might just need to turn the screen just around a bit so she can see what we're doing over here with the calculator. I'll just move that and I'll try not to write on that side of the screen. So we're over here on our calculator here. It's probably hard to see. Let's just get an approximation for e. So we'll just go back to my here and let's just find this. So I've got really 1 plus 1, yeah, plus 0.5, which is a half, yeah, plus 1 divided by 3 factorial, which is 6, good. Plus 1 divided by 4 factorial, which is 24, isn't it? Yeah. Equals 2. There's my approximation for E. Now what is E? E is going to be that. So how close are we? Well, we're not that close. Is there a way to improve this? What would you do, Vincent? I would probably go back to this here and I would grab that if I can. Control C, I'll paste this down here and I'm going to add on 1 divided by 5 factorial, which I'll just write 5. I think factorial's here, isn't it? 5 is, where's factorial? I think there was factorial in here somewhere, wasn't there? No! I've got to go to, does anyone know where factorial is? I do. One way to get it is menu, probability. Hang on, my calculator's, I'll just go back. Probability, and we want, what do we want? Factorial? There it is there. There is another way to get it, I'm not sure why that's not there. And enter, and as you can see, I've improved my guess very quickly by adding on an extra term, haven't I? You can see there, here is 5 terms, 1, 2, 3, 4, 5, 6, sorry, 6 terms, and look how close that term has got. It's taken it from, really, we're 0.001 out. Now look how close we are. Really, really close. So imagine if I was to add on a few more terms, which is what your calculator does, to get a very good approximation of E. Now your calculator can do this very, very, very easily and quickly. So often some of the algorithms built inside your calculator are just Maclaurin series. That's how it gets E. That's how it gets sine of a whole lot of numbers, which we'll do. So let's look. So there's the expression for E. Can we write that in a sum form? Can we write e to the x as a Maclaurin series in sum form? Yes, we can. So e to the x is equal to the sum from 0 to infinity of x to the power of k divided by k factorial. Hey, who remembers? We did this in our last class. Who remembers finding the radius of convergence of that? I do. Can you go back in your notes? Remember we did this, it was our second example. Go back yesterday and look at the second example that we did. Was this one, wasn't it? Can anyone remember what's the radius of convergence? What does this series converge? That series will converge to all values. It will converge for all values of x. So it doesn't matter what value of x we put in, that series will converge. So this series will converge for x is an element of all real numbers. Goodyo, hey, let's do sine. Let's do sine x, shall we? How do we get it? Now, this is in your textbook. So do you need to remember that? No, sorry, it's in your data book, not textbook. This is in your data booklet. Do you need to remember that? No, you don't. But of course you won't forget it. Now I've shown you what it is. And also we use this later on when we develop an expression for what's called a Poisson distribution, which is a probability distribution that we're going to use later on. So we'll use this Maclaurin series to help develop a formula for that. But let's go and quickly look at sine, and then let's choose one out of the textbook so that we're well versed in how to use a Maclaurin series. Then I want to just quickly draw some graphs and show you how adding on more and more, taking a higher degree polynomial actually produces a more accurate expression for the function that we're trying to find. I'll show you that in a moment. But let's just have a bit more practice. Let's do one for sine. So f of x is equal to sine x. And then I'll just choose one out of the back of the book that involves a little bit more differentiation. But we'll do this first of all. So we need to write a Maclaurin series. What is a Maclaurin series? Ready? Here we go. F of x equals to f of 0 plus f dash 0 x plus f double dash 0 x squared on 2 factorial plus dot 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 dot. So there's the general expression for a Maclaurin series. What do? We've got to find, are you ready? What's f of 0 equal to, Susan? F of 0 is? 0. Voila, very good. What's f dash x equal to, everyone? Cos x. What's f dash 0 equal to? 1. Very good. What's f double dash x equal to? Minus sine x. F double dash 0 equals to? Minus 0, which is 0. Good. F triple dash x is equal to minus cos x. What's f triple dash 0 equal to? Minus 1. Ooh, can we see a pattern here? Every even derivative is 0. Every odd derivative is 1 and then negative 1. So what sort of series is this? 1, negative 1, 1, negative 1, 1. It's alternating, isn't it? It's alternating at odd powers. So I think straight away some of you can see this, so I'm just going to jump straight into it. F of x equals 2. Now we can see this is odd powers here. So there's an odd power, that's 1 times x, so my first term is x. What's my second one here? So I miss this one, and then I jump to the next one, which is x cubed. However, x cubed is going to be a negative, isn't it? So that's going to be minus x cubed on 3 factorial. What's the next term, Xavier? Plus x to the power of 5 on 5 factorial. Why not x to the power of 4? Because if I take the fourth derivative, if I go the fourth derivative of, if we differentiate cos, we get minus sine. We're going to end up with, the fourth derivative is sine x. What's the fourth derivative? 0 is 0. That's why that's disappeared. That's why we only have odd powers. What's my next term? Minus x to the power of 7, very good, on 7 factorial. And ladies and gentlemen, this one's in your data booklet too. And it's also a question in your textbook to do with radius of convergence. Find the radius of convergence. This also converges. If you do a ratio test on this, which we have written the sum, you'll find this converges for all values of x as well. So, phi bar, what's my expression? Start at 0, will we? Yeah. Well, we could start at 1. We'll start at 0. So what's this going to be? This will be x to the power of, was it? 2k plus 1? Yeah. Divided by? So when k is 1, it's this one. When k is 2k plus 1 factorial. Well, I'm not sure that's going to generate this, because if k is equal to 2, 2 times 2 plus 1 gives me 5, doesn't it? Pardon? K plus 2. No. No, because if k was equal to 2, then it'll be 4. 2k? Yeah, but how do I get this one here then?
Isn't that 0? Isn't that the first term starts from 0, right?
The first term starts at
0.
Yeah, so this is 0. Yeah, I mean, I agree. I'm just trying to tease something out. I mean, I'm just trying to say that, what are we going to do? I mean, there's a few things. We could start this at 1. Yeah? We Agreed. So we could start that at 1 and say that that's 2k minus 1. It's probably the easiest thing to do, isn't it?
The textbook they did 2k plus 1.
2k plus 1
Yeah.
and start at
0. But they add the negative 1 to the power of k in front.
what did they do? Oh yes, of course, because guess what, ladies and gentlemen? Guess what we've forgotten to do? We need to add a sign generator on. Yeah? So let's do the sign generator first. What's my sign generator going to be? Negative 1 to the power of k, is it? Yeah, that'll do. And then, so when that's 0, yes, that's going to work. And then what's my x raised to the power of?
2k plus 1. Over 2.
But I don't think that's going to work, is it? When we're at 1, yes, of course it's going to work, Mr. Stewart, you crazy man. Divided by 2k plus 1 factorial. Thank you. And if you were to do a ratio test, that would converge too. And that's also in your data booklet. When k is equal to 0, when k is equal to 0, then we get this one. If k is equal to 1, we get 3. If k is equal to 2, we get 5, and so on. We just got to make sure we generate them. Hey, what do you think the expression is for cos? Do you know what we call this? Sine. Do you remember why we call, is sine odd or even? No, sines are odd function. Another, if you like, reinforcement of the fact that sine is an odd function is, look. Why is sine an odd function? Who remembers why sine's an odd function? F of negative x equals to negative f of x. Yeah? But if you like, there's another, well, I'm not sure if this is the reason for it, but isn't it interesting that sine as a polynomial has odd powers of a polynomial? Does cos have even powers? Should we do the cos one? Yeah? Just quickly, let's do cos and you'll see that very, very quickly. F of x equals to cos x, yeah? So what's f of 0? F of 0 starts at 1, very good. And then we've got f dash x equals to minus sine x. So f dash 0 equals to 0. F double dash x equals to minus cos x. So f double dash 0 equals to minus 1. I think you can see the pattern, can't you? Yeah? Here's 1. Here's minus 1, the next one's going to be 0, then the next one's going to be 1, the next one's going to be 0, the next one's going to be minus 1. So our Maclaurin series for cos will be f of x equals to 1 minus x squared on 2 factorial plus x to the power of 4 on 4 factorial, which plus dot dot dot, which equals to the sum from 0 to infinity. Again, we need our sign generator. Minus 1 to the power of k. And then I'll have up here what? It will be x to the power of 2k divided by 2k factorial. Again, if you like some further reinforcement of the fact that, if you remember, cos is a even function. Do you remember the definition for an even function? F of negative x is equal to f of x. Right. Sorry, I know you're all very tired, but I need you to practice one. I'll choose one just out of the book. I'm on page 102. Can you please do C1? Do you know what? I might make you do C2 to show you how tricky this can... No, C1's fine. Yes, C1's good. Yes?
Well, that is odd function.
Oh, well, I'm just odd. It's odd from early in the year, if you remember.
Yeah, that's f like 2x equals 9.
Yeah, well, I'm just saying it's interesting that sine is an odd function and these powers are odd. There's no, it's just, I'm just trying to say, oh, it's another kind of way to remember that those powers are odd for sine and the powers are even for cos, because of when we talk about function theory. Yeah, cos is an even function, sine is an odd function. Completely irrelevant reasons, perhaps. Perhaps. Not really, it's not really. There is a reason why that. Because of course, an even function must be made up of things that have symmetrical. Remember, x squared is the same on both sides. X to the power 4 is the same on both sides. So if you like, that's a reason for it. Okay, which one did I say? C1, the first non-zero terms. Can I rub out? What can I rub out? Let me rub out this. Do you have a piece of paper, Vincent? Good. Can you do this one then? I want the first what? You going?
No, I don't know how quickly.
Are you seriously going?
No, I'm not going.
Oh, good. Piece of paper, guys. Do you have a piece of paper, Nathan? David, grab a piece of paper, please. Can you find the first 4 non-zero terms in writing that as a Maclaurin series, which is a function around the point x equals 0. Quickly, let's go. Can I do it too? I'll give you 3 minutes head start. And then I'm going to come and do it. Almost finished, you think? Almost finished. Not much longer to go now. Sorry, I'm just thinking. Good. Good. Then you've got to find f dash x. Well done. Good. Everyone's off and running, so I'll start too, yeah?
2G 乘以根号加1加 x 分之1不是有2分之一，后面那个数因为 x 等于0，所以永远都是1。
So it says find the first 4 non-zero terms. So that's a non-zero term, this is a non-zero term, that's a non-zero term, and that's a non-zero term. Susan, one of the problems here with doing this is, guess what? This is quite an easy one, but sometimes this differentiation is going to get harder really, really quick. Yeah, the ones in the exam can be really hard to quick. Yeah, so you need to practice those past exam paper ones. Yeah. You're not going to get one that easy, no way. Right, unfortunately, they're really tricky. And these start to just grow, you know, because you've got to use a product rule. And then they grow in terms, and then you've got to collect terms. Oh my gosh, they can be really tricky. Anyway, you'll see them when you practice the exams, yeah? But yeah, this is a relatively straightforward one. Am I finished, everyone? Yeah, I'm finished straight away. So, I've really got f of x is equal to 1 plus, yeah, x on 2 minus x squared on 4 times by 2 factorial plus 3x cubed on 8 times by 3 factorial, and they only ask for the first 4 non-zero terms to approximate this. So we get f of x equals to 1 plus x on 2 minus x squared on 8 plus 3x cubed on 6 times 8 is 48. Okay? And that's my Maclaurin series for that. It's that easy. But as I said, you're not going to get one that's necessarily that easy to differentiate. Yeah? Yeah. Maybe let's do all the theory first, then I'll try and show you a couple from past exam papers. Okay. What I want to do is I want to steal a little bit from tomorrow's lesson, so when we come into tomorrow's lessons, there's a chance that we could do tomorrow's lesson and maybe a little bit more into that next. I want us to finish all of this week. Even if I have to make a video over the weekend and post it up for you, we're gonna finish this week. But just before you go, I just want to show you a bit of magic. And it's not magic, but you can sit back and relax. I want to show you what happens with sine. Do you remember sine x? Sine x can be approximated using the odd function. What was it? X minus x cubed on 3 factorial plus x to the power of 5 on 5 factorial, so on, yeah? I just want to show you how, as you add on more terms, yeah, it starts to actually shape to a sine curve. I think this is quite magical, yeah? So maybe I could even move this over a little bit closer for Om to see. Is that all right? I'll just move that there, just so she can see exactly what's happening here. Let me just get up my calculator. So I've finished. So if you can just watch here, I think you'll really like this. So what I'll do is I should already have sine up here. Okay. So there's sine x, right? Could even stretch it a little bit more. In fact, look, I might stretch it just to. I'll stretch this here to minus 5. And I'll stretch this to 5 and press OK. Right, so I've just stretched a bit. Okay, let's quickly show you what would happen. So I've just got to go tab, don't I? Tab. Let's put in just the first one. Sine x is equal, if I was to use one term of a Maclaurin series for sine x, what is it? X, very good, thank you. How accurate is this? Well, you should all know from your physics and from your maths that sine x is approximately equal to x, which is approximately equal to tan x, which is a very commonly used approximation for lots of physics stuff. Yeah, it's called the small angle approximation. Some of you might be doing that. Sine x is approximately equal to sine x when the angles are less than 10 degrees. And tan x also comes up here as well. So often in physics, if we have a sine x, because it's really complicated, we just get rid of it and we put in x. Now you might remember that for those who are doing physics, sine theta equals to m lambda divided by d. Yeah? What do we approximate sine theta with? You approximate it with x. Yeah, or tan, don't you? Tan. Tan theta, or you can approximate it with x as well. Okay, so you do that when you do your interference stuff. You know, let me just get back here. Let's add on two terms. So x is not a bad approximation, very, very close to 0. It's almost perfect. Way from 0 though, it starts to not be. But all we have to do is go to my tab and let's go x minus, what was it? X minus x cubed divided by 3 factorial, which is 6. Let's have a look and see how this works. There you go. Nice, isn't it? The black line is even more accurate. Yeah, it works really, really well. There's 0.2. So up to about 1 radian or 1, it's actually really good. So there's a cubic function in here. Yeah, modelling that sine graph. Let's now go to a 5th order polynomial and see how accurate that is. Yeah. So let's keep adding on higher terms. What's happening as we're adding on higher terms? We're getting more and more accurate to my original function. The accuracy is also improving the further we are away from x equals to 0, isn't it? Remember, where does this Maclaurin series based around? X equals to 0. So as we add on more terms, yes, it's getting closer and closer to the function. But in addition to that, the error, the difference from this function and to my true function, is getting less and less the further away from x I am. Okay? So as I get further away from x, you can see the first estimate was there. This is there, the error. So there's an error, isn't there? There's an error in approximating sine away from x equals to 0. But the more terms I do, the better that gets. Let's just add on one more term just to see how we go. Hey, maybe I'll add on 2 terms. Yeah, because we sort of know what's going to happen. So let's go here to the tab and let's just add on x and minus control, isn't it? Control. Yeah, this will be x to the power of 3 divided by 6. Divided by 6. And the next one is minus plus, yeah, I better go back. This is x to the power of 5 on 5 factorial. Yeah, I better do this. So it's 5 menu. No, not. It is menu, isn't it? Escape. How do I get factorial up there? Where is factorial again? It's got to be in here, isn't it? No. Yeah. 120. 28. 20. Oh, you're good. Plus, what's the next one? What's 7 factorial?
That's minus.
Plus and the minus.
Yeah. Okay. Let's do this one. I'm almost. Let's go here. I'm making x to the power of 7 divided by what's 7 factorial? I don't know. 120 times 6 times 7.
5,040.
1,000 and?
5,040.
5,040. I knew that. Yeah. Let's see how accurate this is. Yeah. Well, there we go. Good, huh? Really, really accurate now. So that's using a 7-degree polynomial. And you can see, look how accurate, this is pretty accurate up to where? Yeah, it's almost accurate, it's very accurate up to pi. Beyond pi, it's starting to lose its accuracy. Do you see what I mean by that? Yeah. Now, in the next class, guess what I'm going to do? I'm going to say sine x is equal to this, and I'm going to put on the end what's called Rn. Do you know what we call Rn? It's called, well, what do you think it is? Come on.
Infinity.
No, it's my error term. It's an upper bound for what the error in using a Maclaurin series to a certain degree is? Yes? Obviously, if I have a higher degree, what happens to this area? Yeah, well done. Smaller degree, bigger error. Do I know ever what the error term is? No. If I knew what the error term is, then I'd know what the answer is and there'd be no error. So, is this error term an exact value? No, it's an upper bound. So again, the situation here, in our next class, we're going to talk about this error term. And of course, the error term changes depending on how many terms of the Maclaurin series you use. But, so here's our error term there. This is an upper bound, by the way, too. And you must be sick of hearing my voice. I don't blame you. Do you want a bit of homework? Yes, you do. I can hear you. I really think it would be a good idea, and I think, Brian, this is the one you'll see. Can you do, please, 1C2. So please make sure you do this over here. I'll just bring you back in here. So please make sure you practice some of these. So for homework, please, can you do 1C2 is a really good one. I really think you need to do D1, which is tan x. This one is 1 on 2 minus 3x all squared. And I really think you need to do 2 and 3. Why? Because you get an inkling of how hard this can be as the terms get more and more tricky. In fact, I really think you probably can do not 3, question 4 please. Don't do 3, do 4. That's enough. A little bit each night please. Make sure you do that, or otherwise it's going to make it really hard when we go on in tomorrow's class. See you all later. See you.